we present tracing versus freehand, an analysis using a new dataset to understand similarities and differences between tracing and freehand drawing, as well as to evaluate computer-generated drawing approximations. The computer graphics community has long been interested in developing methods to approximate what people draw. Computer-generated drawing approximations are often used as a proxy for hand drawings. However, the extent to which current CGDA results resemble real drawings remains unclear. In particular, most CGDA methods only approximate the end result, neglecting the drawing process, which includes stroke and temporal information. We consider two common forms of drawing, tracing and freehand. Tracings are easier to obtain than freehand drawings and are registered to images by definition. The art community has long discussed the distinction between them, but there is a lack of quantitative analysis. There have been quite a few datasets that provide insight into drawing, but they are not readily applicable to the comparison between tracing and freehand drawing. In our study, we included 100 photorealistic images with wide variations in appearance and content as prompts. We collected 1,210 tracings from 96 participants and 288 freehand drawings from 19 participants. We register freehand drawings using a course-defined optimization of image correlation between freehand drawing and tracing density using IEEE. We start our analysis by exploring whether people trace and draw similar content using rasterized drawings. We computed PyRest distances to understand what people draw in common. For each pixel in a drawing, we recorded its closest distance to any pixel in other drawings. In both tracing and freehand, over half of the distances are within 4 pixels. This corresponds to commonly drawn content such as contours. About 15% of the distances are 20 pixels or more, which represents strokes distinct from each other. We obtain drawing density by superimposing all tracings and all registered freehand drawings for each image prompt. We then obtain binary commonly drawn regions by thresholding the density maps. Tracing and freehand drawing have similar CDR. Between them, over 80% of the PyRest distances are within 4 pixels. We found that over half of the pixels are common content in either form of drawing. People also draw similar common content between tracing and freehand drawing. We observed that this mostly occurs as silhouettes and interior contours of objects. To understand when people draw these common pixels, we divided the temporal span into 25 bins and counted the number of CDR pixels as well as pixels drawn within each temporal bin. We found that in both tracing and freehand, the number of all pixels drawn is mostly uncorrelated with time. However, people tended to draw more common pixels early, and this tendency is stronger in tracing. We are also interested in how people's spatial focus changes over time. For CDR pixels of each prompt, we recorded their XY coordinates and their distance to the barycenter of the drawing. In tracing, this C decreases over time in 90% prompts, suggesting an outside to inside behavior. In freehand drawing, Y increases over time in 84% prompts, suggesting a top to bottom behavior. To understand this as a finer scale, we divided the temporal span of each drawing into 10 equal bins and took snapshots of the drawing in progress. We computed the convex hull area of each snapshot relative to that of the final drawing. We found that people tended to cover larger areas earlier in tracing. To sum up, people preferred finishing the entire outline first in tracing, as opposed to decomposing the prompt into parts in freehand drawing. This difference is more obvious when the prompt contains facial features catching artists' attention. The raster representation showed what people draw in common, but it missed stroke information. We now look into whether people use similar strokes using recorded vector data. We observed more flexible behaviors in freehand drawing. People tended to draw more strokes and also pause more, possibly because they needed to consider proportions. Overall, people drew similar amounts of content, but overdrawing is more common in freehand drawing. Stroke length is more evenly distributed in freehand drawing. This agrees with our observation. When tracing, people tended to draw long strokes as silhouettes, followed by much shorter shading strokes. To examine trends in the drawing process, we evaluated a list of heuristics for stroke ordering. For each drawing, we performed a Monte Carlo sampling of all possible orderings. We then computed a score for each heuristic as the percent of random orderings whose energy was above that of the ground truth ordering. We found that overall, these heuristics characterize stroke ordering better in freehand drawing. Proximity is most important for both. Collinearity comes second and is less important in tracing. Simplicity is not as effective. People don't necessarily start with straight or constant curvature strokes. To further understand whether people use similar strokes in the drawing process, we extracted a list of stroke features and examined how they changed over time. We observed that in both tracing and freehand, stroke length, duration, and opacity tended to decrease over time. Speed and stroke width tended to increase over time. An inconsistency with pressure, people tended to apply more pressure when they started tracing contours than drawing them on a blank canvas. To sum up, we found that in both tracing and freehand drawing, early strokes tended to be long and drawn slowly using opaque colors. Late strokes tended to be short and drawn quickly using translucent colors. Changes in stroke features over time indicate that people might employ multiple types of strokes over time. Therefore, it is important to understand if tracing and freehand drawing evolve similarly. We manually labeled over 14,000 strokes in all tracings and freehand drawings for 10 prompts. We used two main categories, geometric contours and tone details. Geometric contours are further divided into silhouettes, interior contours, ridges, and valleys. Tone details are further divided into hatching, stipple, and texture. Overall, we observed that drawings progress similarly in tracing and freehand drawing. Silhouettes were dominant at the beginning, and hatching strokes became more prominent towards the end. Trends in how stroke features and labels change over time suggest the possibility of stroke classification. We built random forest classifiers using these features. The classifiers distinguish geometric contours from tone details with an accuracy of about 80 to 90% on splits of prompts, drawings, and strokes. Here we show sample label tracings used for training the classifiers. Orange represents geometric contours and blue represents tone details. We trained the first classifier using 80% tracings and tested it on the remaining tracings. We can see that the prediction is very similar to the ground truth. We also trained another classifier using all tracings as training data and tested it on freehand drawings. The classifier was still able to predict a correct label for most strokes. To sum up, we found that spatial temporal stroke features can effectively characterize drawing intention. Classifiers learned from tracings can be transferred to freehand drawings. We now revisit current CGDA methods and evaluate their output using our data to see how similar drawing content is to computer-generated output. We begin with a pixel-wise comparison between rasterized drawings and CGDA results. We computed precision as a fraction of CGDA pixels near any drawn pixel and computed recall the other way around. We considered 5 widely used CGDA algorithms and found about 60% of drawn content is consistent with computer-generated output. As shown here, NPR methods captured contours but did not consider texture information. Some image processing results contained incomplete or extraneous edges. Compared with CGDA results, drawings were cleaner, more organized, and contained interesting strokes that depict tone and shading. We also observed that CGDA achieved different performance on different images. For both tracing and freehand drawing, CGDA achieved lower precision and recall on images containing background. The same trend was observed for images with texture. This agrees with our intuition because NPR typically does not consider image background or texture, and image processing output often includes extraneous edges from background and texture. To sum up, image attributes affect CGDA performance. This shows our dataset's value for identifying extensions to NPR and image processing algorithms that better approximate drawing, such as fusing different algorithms. We now examine how CGDA corresponds to common strokes. For each stroke, we computed the common score using drawing density to measure how well it covers commonly drawn regions. We also computed a CGDA score similarly. In tracing, we can see that early strokes tend to have higher common and CGDA scores. We observed the same trend in freehand drawing. We ran a correlation analysis between both scores and stroke order and between the two scores for all strokes in each drawing. In both tracing and freehand drawing, common and CGDA scores tend to decrease over time, and there is a strong positive correlation between the two scores. To sum up, CGDA methods can capture content that people commonly draw, but not people's diverse artistic conventions. We compared our data with output from an NPR hatching algorithm, as people often depicted tone details using hatching. We composited all drawings for each prompt and blurred it to get areas of dense stroke coverage. We then compared it with the blurred version of NPR hatching. We computed the fraction of pixels in the blurred NPR hatching whose response was near that in the blurred drawing composite and vice versa. We found that less than half of drawn shading is consistent with NPR hatching. The hatching algorithm does not understand the semantics of the prompt, resulting in hatching patterns different from what people draw. The diversity of shading techniques presented in our dataset can inform new NPR hatching algorithms. To conclude, our analysis reviews the similarities and differences between freehand drawing, tracing, and computer-generated drawing approximation. Tracing is similar to freehand drawing in temporal tendencies and representation choices. Spatial temporal features can characterize drawing intention in both tracing and freehand. Current CGDA results only capture 60% of drawn pixels on average, highlighting the great value of collecting hand-drawn data. Our dataset and analysis can be useful for many future applications, such as translation between image and drawing density, data-driven NPR methods that better emulate the drawing process, and recognition of different types of strokes and their customized treatment in sketching interfaces. Thank you for listening.